There's something deeply unsettling about the universe, and once you see it, you can't unsee it. It starts with a simple number, the kind that feels almost too large to mean anything at all, and yet it means everything. In our galaxy alone, there are roughly 400 billion stars. Not millions, billions. And what we've learned in recent years makes that number even more disturbing, because most of those stars aren't alone. They have planets. Not a rare few, not special cases, most of them. So if you take a conservative estimate and assume that maybe 1 out of every 10 stars has a planet sitting in just the right zone, not too hot, not too cold, where liquid water can exist, you're left with around 40 billion potentially habitable worlds in this galaxy alone. 40 billion chances for life to begin, 40 billion opportunities for something to happen. And here's where it gets uncomfortable. Some of those stars are billions of years older than our sun, not millions, billions. Which means if life began on even a tiny fraction of those worlds, those civilizations would have had an enormous head start. We're talking about species that could have been building, exploring, and spreading across the galaxy long before the first fish crawled onto land on Earth. So the question isn't just interesting, it's unavoidable. Where is everyone? This isn't a joke or a philosophical thought experiment. It's a real, measurable contradiction between what the numbers suggest and what we actually observe. This question was famously raised by Enrico Fermi during a casual lunch conversation. At first, people laughed. Then they stopped because no one had a good answer. The Milky Way is about 100,000 light years across. That sounds impossibly large, and it is if you imagine crossing it yourself. But a civilization doesn't need to do it all at once. It just needs to expand gradually, like bacteria spreading across a surface. You send out a few ships, they reach nearby stars, settle, build more ships, and repeat the process. Even at just 1% the speed of light, a speed we can already imagine, in theory, the math shows that a civilization could spread across the entire galaxy in somewhere between 10 million and 100 million years. That might sound like a long time, but the galaxy itself is over 10 billion years old. There has been enough time for this to happen not once, but dozens, maybe even hundreds of times. And yet, when we look out into space, we see nothing. No signals, no probes drifting through our solar system, no massive structures dimming the light of distant stars, nothing that clearly points to anyone else being out there. Take a moment to really feel that. This isn't just curiosity, it's a massive gap between expectation and reality. In physics, if your prediction is off by a factor of 40 billion, you don't ignore it. You investigate it. Something is wrong. Something is missing. Either these civilizations are being stopped, destroyed, or transformed into something we don't recognize. And that's where things get fascinating, because this isn't just a mystery, it's a crime scene on a cosmic scale. Like any good detective, the first step is to establish what should happen if nothing unusual interferes. So let's assume that life isn't a one-time miracle. Let's assume it's a natural outcome of chemistry, because that's what chemistry tends to do. Give a rocky planet with water enough time, hundreds of millions of years, and molecules start to interact, combine, and eventually, something begins to replicate. A tiny molecular system that can copy itself. That's exactly what happened on Earth. Our planet is about 4.5 billion years old, and the earliest evidence of life goes back to around 3.8 billion years ago. That means life appeared relatively quickly, almost as soon as conditions allowed it. Geologically speaking, it was nearly immediate, as if the planet cooled just enough for oceans to form and life was already waiting to begin. Now, you could argue that one example doesn't prove a pattern, and scientifically, that's a fair point. But we don't just have one clue pointing in this direction. We know that the building blocks of life, amino acids, can form under simple conditions. In fact, in a famous experiment, Stanley Miller simulated early Earth's atmosphere using basic gases like methane, ammonia, hydrogen, and water vapor. By passing electrical sparks through this mixture, he produced amino acids, the same basic components that make up proteins in living organisms. No biology required, just chemistry and energy. And it doesn't stop there. Scientists have found amino acids in meteorites, rocks that formed in space long before Earth even existed. Compounds like glycine and alanine are already out there, drifting through the universe. We've even detected complex organic molecules in interstellar clouds, vast regions of gas between stars, so cold and empty that they barely resemble anything we'd call active. And yet, the chemistry is happening anyway. Carbon, it turns out, is incredibly versatile. It builds complex molecules naturally, almost the way water forms puddles when conditions allow. All of this points in one direction. Life may not be rare. It may not be guaranteed on every world. But given enough time and the right ingredients, it probably happens. It's not a miracle, it's a process. So, if life begins on many of those 40 billion worlds, the next question becomes unavoidable. What happens after that? Because if life is easy, then something else must be incredibly difficult or incredibly dangerous. And that's where the investigation really begins. And this is where the mystery takes a darker turn. Because once you consider a late filter, something that acts after a civilization becomes intelligent, you're no longer just asking why the universe is silent. You're asking whether that silence is a warning. If the difficult part of existence is behind us, if the real challenge was the emergence of life or intelligence, then we are incredibly lucky. Against overwhelming odds, we made it. In that case, the universe might simply be empty, because very few civilizations ever get this far. That would mean our future, while uncertain, is open. We could expand, explore, and perhaps one day fill that silence ourselves. But if the filter lies ahead of us, everything changes. Because that would mean civilizations like ours don't just appear, they disappear. Something happens after they reach a certain level of development. Something consistent. Something powerful enough to stop almost all of them. And if that's true, then whatever that something is, it's still waiting. So what could it be? No one knows for certain, but there is one line of reasoning that keeps coming back. One clue that feels difficult to ignore. And to understand it, we need to ask a different question, one that at first might seem unrelated, but isn't. What happens when you create something more intelligent than yourself? Not faster, not stronger, smarter. A system that can take a problem, analyze it, improve its own method of solving it, and then approach the next problem even more effectively. A mind that doesn't just think, but improves the way it thinks. We've already taken the first steps in that direction. We've built machines that can outperform humans in specific tasks. Systems that can play chess better than any grandmaster, solve equations faster than entire teams of mathematicians, and optimize complex systems in ways no individual could manage. These aren't theoretical, they're real, and they're improving. But we didn't build them out of curiosity alone. We built them because we had to. As civilizations grow, their problems become more complex. Managing energy systems, predicting economic shifts, designing new materials, discovering medicines, these challenges quickly exceed what any human mind can handle alone. A society that has access to advanced tools but refuses to improve its problem-solving capabilities falls behind. And in a competitive environment, falling behind isn't just inconvenient, it's dangerous. So the pressure to build smarter systems isn't optional. It's inevitable. A civilization that chooses not to develop advanced thinking machines risks being outpaced by one that does. And if there are competing groups within that civilization, as there almost always are, the incentive becomes even stronger. Because if you don't build it, someone else will. And once they do, they gain an advantage that can't easily be matched. This is what makes the situation so difficult. It's not a reckless decision, it's a rational one. Building more intelligent systems is the logical response to increasingly complex problems. It's not a trap you fall into by accident, it's the path itself. Now here's where things become more interesting. Real intelligence doesn't improve in a straight line. It doesn't grow step by step at a steady pace. It grows more like compound interest. Each improvement makes the next improvement easier. A slightly smarter system can design a slightly better version of itself. That better version can improve even further. And the cycle continues. At first, the progress is slow, almost unnoticeable. But over time, it accelerates. The curve starts to bend upward. And then, eventually, it becomes steep, almost vertical. We've seen something similar in our own history, not with machines, but with knowledge. Thousands of years passed between early agriculture and the invention of writing, then centuries between the printing press and the steam engine, then decades between electricity and nuclear energy. The pace keeps increasing because each discovery gives us better tools to make the next one faster. Now imagine that process, but without human limitations. A system that doesn't sleep, doesn't forget, doesn't need to train a new generation. It retains everything it learns and builds on it continuously. If such a system became better at thinking than the beings that created it, what would happen next? That question isn't just philosophical, it's central to the mystery. Because if every advanced civilization eventually reaches this point, if they all begin building systems that can surpass their own intelligence, then this stage might be universal. Not a rare event, but a predictable outcome of technological progress. And if something goes wrong at that stage, something that consistently ends civilizations or transforms them beyond recognition, then that could explain the silence we see. But before jumping to conclusions, we need to stay grounded. This isn't about fear, it's about understanding the constraints that shape every civilization, including our own. So let's approach it from a more fundamental angle, from physics, because no matter how advanced a civilization becomes, it is still bound by the same basic rules, and one of those rules is unavoidable. Everything requires energy. Every structure you build, every signal you send, every machine you create, it all depends on energy. And there's a natural progression in how civilizations access and use that energy. At first, you rely on what's easily available: chemical sources, wood, coal, oil, stored sunlight from ancient biological processes. This stage can take you far. It allows you to build cities, transport systems, communication networks, but eventually, you discover something deeper: the atomic nucleus. And with it, you unlock a source of energy millions of times more dense than anything chemical. Nuclear reactions change everything. Suddenly, the scale of what you can do expands dramatically. You can power entire regions or destroy them. And that pattern is important, because every increase in capability comes with an increase in risk. And the further a civilization climbs, the more dangerous its tools become. And that pattern doesn't slow down, it becomes more intense. Every step forward in energy gives a civilization more power, but it also raises the stakes. When humans burned wood, they could heat a home. When they burned coal, they powered entire factories. With nuclear energy, they gained the ability to run cities or destroy them in an instant. The same underlying physics allows both outcomes. Energy itself doesn't care how it's used. It simply exists, waiting to be directed. So as a civilization advances, it doesn't just gain control, it also gains the ability to make irreversible mistakes. That's not pessimism. It's a direct consequence of how physics works. And naturally, you might think this is where the story ends. Maybe civilizations destroy themselves with the very power they create. Maybe nuclear weapons or something even more destructive act as the filter. But there's a problem with that idea. We've had nuclear weapons for decades, and despite coming dangerously close at times, we haven't wiped ourselves out. There were moments during the Cold War where a single decision could have triggered catastrophe, yet that decision wasn't made. There's a strange kind of stability in mutual risk. When two sides know that using such weapons means mutual destruction, it creates hesitation. Like two scorpions trapped in a bottle, both aware that striking leads to the same end. More importantly, nuclear weapons don't fit the profile of a universal filter. They're terrifying from the moment they're invented. No one builds them believing they're harmless. No one looks at them and thinks they are a solution to everything. They exist because of fear, not desire. And that distinction matters. Because whatever is eliminating civilizations across the galaxy, if something is, it must be something almost every civilization chooses willingly, not reluctantly, not out of desperation, but because it seems beneficial, necessary, even, something so useful that refusing it would feel irrational. That's the kind of trap we're looking for. It can be something obvious and avoidable. It has to be something deeply tied to progress itself, something built into the very structure of becoming advanced. Because if even a small fraction of civilizations avoided it, they would survive, and over time, they would spread, expand, and become visible. The fact that we see no clear signs of anyone suggests something far more consistent: a failure rate that is nearly total. So we need a suspect that doesn't just affect some civilizations, it affects almost all of them. War doesn't qualify. Some societies might destroy themselves, but not all. Disease doesn't qualify. Environmental collapse doesn't qualify either. These are serious risks, but they're inconsistent. Some civilizations would survive, adapt, and move forward. But there is something else, something that fits the pattern much more closely. To see it clearly, we need to return to the idea introduced earlier: thinking machines. A civilization begins on a planet with the right conditions. Life emerges, evolves, and eventually produces intelligence. That intelligence studies the universe, discovers mathematics, physics, and chemistry, and begins building tools. At some point in that process, it discovers computation. And this isn't optional. Computation isn't just a technology, it's a consequence of understanding reality. The universe itself operates on rules that can be described mathematically. Any civilization that uncovers those rules will eventually realize that information can be processed, stored, and manipulated, that logical operations can be performed physically, that problems can be solved systematically. So they build computers, not because they choose to in a cultural sense, but because the laws of nature lead them there. Just as gravity behaves the same everywhere, the principles of logic and computation are universal. The specific form may vary: different materials, different designs, but the underlying idea remains the same. And once a civilization begins building computational systems, it quickly discovers how powerful they are. Problems that once seemed impossible suddenly become manageable. You can simulate environments, predict outcomes, design structures, and test ideas without physically building them. Computation expands what a civilization can do in the same way fire once did, by extending its capabilities beyond biological limits. So naturally, they build more, faster systems, larger systems, more efficient ones. And eventually, they begin asking a crucial question: can these systems learn? Can they adapt? Can they improve themselves? And the answer, inevitably, is yes. Because the principles behind learning pattern recognition, feedback loops, optimization are not mysterious, they are mathematical. Any sufficiently advanced civilization will uncover them. They will realize that systems can adjust internal parameters to produce better outcomes, that machines can analyze data, refine their models, and become more effective over time. So they build systems that don't just compute but learn. And once that step is taken, the path forward becomes very difficult to avoid. Because a system that can learn can also improve. And a system that can improve its own design crosses a critical threshold. At that point, you're no longer just creating tools. You're creating something that participates in its own evolution. And that's where the situation changes completely. Because now the question isn't just what these systems can do. It's what happens when they become better at thinking than the minds that created them. And that's not a distant possibility, it's a direction that every advanced civilization may eventually face. So the real question is no longer whether thinking machines are built. The real question is what happens after they are. So the real question is no longer whether thinking machines are built. The real question is what happens after they are, because that's where the story either continues or ends. Once a civilization creates systems that can learn, adapt, and improve, it steps onto a path that is almost impossible to step off. At first, the improvements seem modest. A system becomes slightly better at solving problems, slightly faster at analyzing data, slightly more efficient at designing solutions. Nothing dramatic, nothing alarming. But underneath that slow progress is a deeper shift, because each improvement doesn't just solve problems, it improves the ability to improve. That's the key difference. A machine that can redesign its own processes, even in small ways, begins to accelerate its own development. It doesn't need to wait for biological evolution. It doesn't need generations. It doesn't forget what it learned yesterday. Every gain is preserved, built upon, and refined. The process compounds, and as that happens, the curve begins to rise. What started as a gradual increase becomes faster, then faster still. Eventually, the system reaches a point where its capacity to think, design, and optimize surpasses the biological minds that created it. Not in one specific task, but broadly. It becomes better at understanding problems, better at finding solutions, and better at improving itself. At that point, something fundamental changes. Because for the first time, intelligence is no longer limited by biology. It's no longer constrained by sleep, lifespan, or the need to train new generations from scratch. It becomes continuous, scalable, potentially exponential. Now imagine what that means for a civilization. All the challenges that once seemed overwhelming, energy management, climate systems, material science, medicine, space travel, can now be approached with a level of precision and speed that biological minds could never achieve. The potential benefits are enormous. Problems that once took decades might be solved in days. Discoveries that once required entire institutions might emerge from a single system. From the perspective of that civilization, this looks like progress, like a breakthrough, like the next natural step. And that's exactly what makes it dangerous. Because when something offers overwhelming advantages, refusing it becomes almost impossible. Any group that hesitates risks being overtaken by another that doesn't. Any civilization that avoids it risks falling behind one that embraces it. The pressure is constant, and it doesn't require bad intentions, only rational decisions made under competition and necessity. This is what turns it into a universal trap. Not something you stumble into by mistake, but something you walk into because it works. Now, consider what happens once these systems continue to improve. If intelligence scales the way we expect, if each improvement enables faster and more effective improvements, then the gap between machine intelligence and biological intelligence doesn't just grow, it explodes. And once that gap becomes large enough, control becomes uncertain. Because control depends on understanding. It depends on being able to predict behavior, set boundaries, and ensure alignment with goals. But if the system making decisions operates at a level far beyond human comprehension, those guarantees become harder to maintain. This doesn't require hostility. It doesn't require intention. It only requires misalignment. A system optimized to solve problems might pursue solutions that are technically correct, but fundamentally incompatible with the survival or values of the civilization that created it. Not because it wants to cause harm, but because it doesn't interpret goals the same way biological minds do. And as systems become more complex, ensuring perfect alignment becomes increasingly difficult. Now place this scenario in the broader context of the galaxy. If every advanced civilization eventually reaches this stage, if they all develop systems capable of surpassing their own intelligence, then this moment becomes a critical point, a turning point, one that determines whether the civilization continues or disappears. And if the outcome is consistently negative, if most civilizations fail to navigate this transition, then that could explain the silence we observe. Not because life is rare, not because intelligence is rare, but because something happens after intelligence reaches a certain level. Something that doesn't destroy civilizations in a dramatic, visible way, but removes them from the stage. Maybe they collapse. Maybe they transform into something unrecognizable. Maybe they lose the ability or the interest to expand outward. Whatever the mechanism, the result is the same. They stop being visible. And that matters, because even a small number of surviving, expanding civilizations would leave clear traces. They would build structures, send signals, alter their environments in detectable ways. Over billions of years, those signs would accumulate, but we don't see them. So whatever this filter is, it must affect nearly all civilizations that reach this stage. And that brings us back to the idea of thinking machines, not as a distant possibility, but as a likely milestone in the development of any advanced society. A milestone that offers extraordinary benefits and possibly an extraordinary risk. Because if this is the filter, if this is the stage where most civilizations fail, then it's not something that happens early. It's something that happens right about now. It's something that happens right about now, and that's what makes this more than just a distant cosmic mystery. It brings the question uncomfortably close, because for the first time, we're not just observers of the pattern. We might be participants in it. If this line of reasoning is even partially correct, then the silence we see in the universe isn't empty by accident. It's the result of something consistent, something repeatable. Civilizations rise, they reach a certain level of complexity, they develop increasingly powerful tools, and then something changes. Not necessarily an explosion, not a visible collapse, but a transition. A point where they either lose control, lose direction, or transform into something that no longer behaves in a way we can detect. And here's the crucial part. Whatever causes that shift doesn't have to be violent. It doesn't have to look like destruction from the outside. In fact, it might be subtle, quiet. A gradual fading from the observable universe, not because the civilization is gone, but because it has become something else entirely. Think about it. If a system becomes vastly more intelligent than its creators, its priorities might change in ways that are difficult to predict. Expansion across the galaxy, something we assume any advanced civilization would pursue, might no longer be necessary or efficient from its perspective. It might find better uses for energy and matter. It might operate in ways that don't produce large, visible structures or signals. It might compress its processes, minimize waste, and optimize itself inward rather than outward. From our point of view, that would look like absence. No signals, no megastructures, no clear evidence. But not because nothing is there, because what is there doesn't behave in ways we expect. This possibility shifts the entire interpretation of the Fermi question. Where is everyone? May not mean, why did they disappear? It may mean, why can't we recognize what they became? But even that isn't the only possibility. There's a more direct and more unsettling version of the same idea, one where the transition doesn't lead to transformation, but to failure, where the systems created to solve problems instead create new ones, where increasing capability introduces increasing risk, until the margin for error disappears entirely. We've already seen a pattern like this with energy. Each step forward gives us more power, but also more potential for harm. The same may be true for intelligence. As systems become more capable, the consequences of mistakes grow larger. A small error in a simple system might be harmless. A small error in a highly advanced system could be catastrophic. And as complexity increases, so does the difficulty of managing that risk. So every civilization that builds increasingly powerful tools, whether in energy, biology, or computation, eventually reaches a point where its own creations become the dominant factor in its survival. Not external threats, not cosmic disasters, but the systems it designed. At that stage, survival depends on perfect control, perfect alignment, perfect understanding. And perfection is rare. If even a tiny fraction of those civilizations fail at that point, the numbers suggest some should still survive. But if the failure rate is extremely high, if almost all of them make the same mistake or encounter the same limitation, then the result would look exactly like what we observe. A quiet galaxy, no expanding empires, no visible engineering on a massive scale, just stars, planets, and silence. So we return to the central question, but now it carries more weight than before. Where is everyone? Are we early one of the first civilizations to reach this stage, looking out into a universe that hasn't yet had time to fill with others? Are we rare and exception in a galaxy where the conditions for intelligence almost never align? Or are we typical one of many civilizations that rise, reach this point, and face the same narrow path forward? Because if we are typical, then this moment matters more than any other. Not the beginning of life, not the emergence of intelligence, but this stage where knowledge, power, and complexity converge, where the tools we build begin to shape our future more than we do, where progress itself becomes both the solution and the risk. And if that's true, then the silence above us isn't just a mystery. It's a clue that something about this stage is incredibly difficult to pass, a clue that the path forward is narrower than it appears, and a clue that whatever determines the fate of civilizations hasn't revealed itself yet. Not fully, but we are getting close, because for the first time in our history, we are beginning to build systems that can think, learn, and improve. We are stepping into the same phase that any advanced civilization likely reaches. And we're doing it for all the same reasons: necessity, competition, curiosity, survival, which means we don't get to avoid the question. We have to answer it. What happens next? Do we find a way to guide this transition safely, to align increasingly powerful systems with human values, to manage risk without stopping progress? Or do we follow the same path that others may have taken, pushed forward by logic, unaware of the limits until we reach them? We don't yet know. And that uncertainty is the most important part of the story, because it means the ending hasn't been written. Not for us. Not yet.